Hey everybody, it's Dr. J, and today we are talking about Gibbs free energy. Let's talk chemistry. All right, so before we get into Gibbs energy, let's talk about spontaneous processes. All right, so this is basically a process that's going to happen without the input of energy from like an outside source. Okay, and when that is the case, then we have a spontaneous reaction. Okay, so I got a couple of different examples. I'm just going to quickly go over some of these, but these are examples of some spontaneous processes. If you got sodium metal reacting with water, right? No need for other energy, right? It's just going to happen. Combustion reactions, gas, as far as suspension of gas in a vacuum, and then of course salt dissolving into a solution. These are all examples of spontaneous reactions, right? So basically, once again, these are processes that are occurring without any energy needed from an outside source. All right, so for example, if you got a ball at the top of the hill, that ball rolls down the hill. That's a spontaneous reaction, right? That's a spontaneous process, right? No input of energy. That ball went down the hill on its own. Okay, so when we're talking about this, right, we got to mention another law, right? So thermodynamics, second law. The second law of thermodynamics is basically in any spontaneous process, the entropy of the universe will increase. Okay, so we got our entropy of the universe. We understand that that's the system and surroundings combined together. As well as another option of saying second law. In trying to do work, you always lose energy to the surroundings. That's also another case. All right, but essentially, right, spontaneous processes, that means that your universe entropy will be increasing. So now let's talk about Gibbs free energy, or G, or you might hear me say delta G, whatever. We're talking about Gibbs free energy, okay? So this is basically Gibbs free energy is the combination of a lot of different state functions and put together in one. Okay, so in this case, we're specifically talking about entropy. Once again, if you don't know about entropy, check out that video. Temperature and then enthalpy. If you don't know about enthalpy, check out the old video on my Chem 1 playlist as well. All right, so this is a combination of entropy, temperature, and enthalpy explaining, right, whether a reaction is going to be spontaneous or not. That's right. That's what we're using to help us determine these spontaneous reactions. Now, we use the symbol delta G to help us define Gibbs free energy of our system. Okay, so why is it called Gibbs, everybody? Somebody discovered it named Gibbs. Okay, basically his name was J. Willard Gibbs. And he said, okay, I discovered this, so I'm going to name this after myself, and let's call it Gibbs free energy. All right, but essentially this is just free energy. All right, but yeah, if I discovered this too, I would have named the same thing. All right, I would have been like Johnson free energy, Ryan free energy. I would have did the same thing. Okay, so this is Gibbs free energy, and that's the reason why it's called Gibbs. Now, the free, when we're talking about free, that's basically referring to the amount of energy available to do work. All right, once you pay your price to your entropy. All right, so once again, this is the combination of everything. It's taking into account entropy and enthalpy in that case. Okay, so because of that, this is basically the leftover energy after entropy. That's how we could think about the free energy. Okay. Now, a couple of different things. One thing I want to point out, all right, is that this is not given simply by the delta H or entropy, right, being released in a reaction. Okay, so we just want to remember that. Now, this is our Gibbs free equation. Basically, delta G is equal to our change in enthalpy minus temperature times our entropy. All right, so like I said, this is a combination of all three of these state functions into one when we're talking about free energy. And once again, that free energy is just what's left over after everything. So basically, here's what you need to know. If your delta G is negative, then that's going to let you know right there you got a spontaneous reaction. If your delta G is positive, that's going to let you know that it's not spontaneous. All right, so it's a non-spontaneous reaction. So if it's negative, spontaneous, if it's positive, not spontaneous. So let's break this down a little bit further. All right. Because, like I said, we got a couple factors that's impacting, right? Negative or positive. So let's look at this quadrant over here, right? If your delta G is negative, so once again, if you have a negative value for your delta G, that means that you got a spontaneous reaction. So in this case, in order to have a spontaneous reaction, right, in this case, it's all temperatures. That means that I have a positive value for my entropy and a negative value for my enthalpy. All right, so if I got a negative enthalpy and a positive entropy, no matter my temperature, my delta G is going to be negative. All right, and it makes sense, right? In this case, this negative enthalpy, right here, minus whatever the temperature is with the positive value. In this case, it's just going to give you probably a negative value. All right, so that's the reason why your delta G is always going to be negative if your enthalpy is negative and you got a positive value. All right. Now, when we jump on this side, let's say for positive value, if our delta G is positive, then our entropy is going to have to be negative and our enthalpy is going to have to be positive, right? So positive enthalpy, and then we have a negative enthalpy, right? So in this case, it's probably going to give you a positive value for delta G. So because it's always going to be the case here, right? Our delta G is always going to be positive for all temperatures. Don't matter the temperature, right? If your delta H is positive, and if you got a negative value for your entropy, it's always going to be positive. Okay. Now, the only thing that's going to impact, right, your delta G is the temperature. So, if you have a positive entropy and a positive enthalpy, right, you're going to have a spontaneous reaction at high temperatures. Okay, so if you got a high temperature, you're going to have a spontaneous reaction if your entropy and your enthalpy are going to be positive, right, over here. And if your enthalpy and your entropy are negative values, then if you have a low temperature, well, you're going to have a spontaneous reaction. Okay. So once again, spontaneous reaction means that your delta G is going to be negative. So in this case, when I'm saying spontaneous, I'm saying that my delta G is going to be negative. So delta G is negative if it's at high temperatures and my entropy and enthalpy is positive. Delta G is negative, right? So it's spontaneous if our delta G is negative and our enthalpy is negative and we have low temperatures. Okay. So these are, this is a good chart just to pay attention to, but also if you know your values and if you understand what delta G is negative or positive, you should be able to determine it as well. So this chart looks very familiar, right? We talked about enthalpy before. We understand that enthalpy of formation, we could just use the values. Entropy, we talked about entropy before, and we understand these values as well. You could use the same thing. Delta G is also a state function, and we also have the values for those. So you guys know what that means. Just like, right, with enthalpy and entropies, we can calculate delta G using, right, the same format. Right, because it's a state function, we only care about the initial and final values. So in this case, right, we're going to do products minus reactants. So looking at this equation, very similar from before, right, if you looked at the previous videos, magnesium, carbon dioxide gives me magnesium oxide and carbon, right? So instead of using enthalpy or entropy, we're just going to use delta G, right? So we're going to have 0 here, negative 394 for carbon dioxide, negative 570 for magnesium oxide, and 0 for carbon. We're going to do the same stuff, products minus reactants. In this case, the coefficients go in front, 2 times our value of minus 570 plus, right, our 1 mole times 0. And then we're going to subtract that by our reactants, 2 times our 0, of course, and then 1 times our negative 394. And what we see here is we get our entire value for our products minus our entire value of our reactants, right? We're going to do some math here, and then we're going to find out that our delta G is going to be negative 746. All right, so 746 kilojoules. So essentially, if I got a negative value, I got a spontaneous reaction. In this case, this reaction is actually highly exothermic. All right, so when we compare that to delta H, if you remember from last time, if not, it's okay. In this case, a delta H or enthalpy was negative 811 kilojoules, right? For this same exact reaction. That's what we found out, right? And because, we said it was highly exothermic, it makes sense that we should see this negative value because negative values for delta H is going to be exothermic reactions. Now, when we're talking about, right, I see a negative 811 and then I got negative 746, right? What is missing in this count, right, is that 65 kilojoules that's missing between the two, right? Because we understand that energy cannot be created nor destroyed, right? First law, thermodynamics. Well, that missing energy between these two, right, even though it's the same reaction, is that entropy, right? The entropy there, right? So that missing 65 kilojoules of energy, that's what went to entropy there. All right, so now, right, everything we learned is coming together. Right, that's all. Everything that we talked about is coming together. But essentially, everybody, this is Gibbs free energy.